So, in this lecture, I'm going to talk about adiabatic, magnetic, adiabatic, magnetic field, invariance of flux through an orbit, and after that I will talk about magnetic mirroring. So this is my article about which I am going to talk about. So first of all, if a charged particle is moving under the influence of electric field, then equation of motion can be written as now multiplying both sides by the perpendicular, it can be written as this, and this can be written as half mb perpendicular square, because if I take its derivative, then its derivative will be half m 2v dv over dt, and 2 will cancel out with that 2, so it will remain this term again, right? So it is this, it is the perpendicular component of kinetic energy, so that's why perpendicular component of kinetic energy, its derivative with respect to time, is equal to this one. So now the increase in, to find the increase in particle energy over one Larmor period can be found by averaging over one Larmor period. So therefore, the change in kinetic energy, perpendicular component, over one Larmor period is equal to E dot this, and this E can be taken outside and integrating over T. So it's closed over one Larmor period, means over a closed contour. So it's a closed curve, so E, and this can be written as dly dt into dt. This will cancel out with it. So it is E dot dl. These are the vector quantities, right? So if I apply Stokes' theorem, then this can be converted into a surface integral. So it will become del cross E ds. Here, what I did, I have applied the Stokes' theorem. And if I use Maxwell's equations, then del cross E is nothing what is equal to 1 by C curly V over curly T. So what does it mean? It means it is E by C curly B over curly T. It's integral over S into ds. So that means this change in kinetic energy, it is minus E by C surface integral. It is curly V over curly S. Sorry, it's a curly V over curly T. Into ds. But for slowly varying magnetic field, curly V over curly T can be written as omega C over 2 pi del V. So therefore, and here delta B is average change during one period, or we can say that in other words over one orbit, So therefore delta E change in kinetic energy is equal to minus E by C omega C over 2 pi delta P into ds. Here minus this can be taken outside, delta V can be taken outside, and also we have to take its integral, and its integral is nothing but pi RL square, as we talked about earlier lectures also. So it is minus E by 2C omega C RL square delta V, because now this pi will cancel out with this pi, so it is delta V. And in magnitude form, this can be written as delta E over 2C RL square omega C delta B. Now this quantity is nothing, what it is, the magnetic moment. So if it is magnetic moment, then this whole can be written as mu delta B. So this change in kinetic energy is equal to written as either minus E by C or curly V over curly T ds, or it is equal to this one. But as we know from earlier lectures that delta E k is nothing but mu delta B plus B delta mu. So if I compare these two equations, but this is equal to this quantity, but this is equal to this quantity plus additional this quantity. So this is possible if and only if B delta mu is equal to 0, which implies delta mu is equal to 0, and this leads to, this is a constant, this is constant, this indicates that magnetic moment is invariant magnetic moment is invariant even when particles are accelerated in electric field. Field induced by slow temporal variation in magnetic field. And this thing is presented means electric field induced by the slow temporal variation of magnetic field. This is clear from equations that this E dot TL means acceleration. This part is causing acceleration, and this is caused by the slow temporal variation in the magnetic field, as because it is equal to basically it is equal to minus E by C curly B over curly T into ds. So that means these two terms was able to explain the statement. Now under this article, a very interesting application comes out to be, that is magnetic mirroring. And sometimes magnetic mirroring found application in plasma confinement. I'm not going to talk about this plasma confinement. I'm simply trying to explain that what is magnetic mirroring. So for this, let us consider or as we know that magnetic moment of a particle is an adiabatic invariant of motion in slowly varying non-uniform magnetic field. Also, we found that this magnetic moment, its magnitude is nothing but is equal to this, or in other words, sorry, and also we found that this RL is Larmor radius. It is CMV perpendicular over EB, and from here we conclude that it is inversely proportional to 1 by B, or yeah, or we can say that it is nearly equal to 1 over B. So that's what we are getting. So what does it mean pictorially? Or we can say that the radii of circle, from this what we are concluding, that the radii of circle on which particle moves decreases in the direction of increasing magnetic field along z-axis, because field is increasing along z-axis. So as so pictorially, how it can be written or how it can be understood, this is like this. It was such type of situation, and say it is z-axis, and say it is the direction of pz, and this is basically vr. So the field is along this direction, and as we already stated, so that means if particle's velocity somewhere is along this direction, and if it is making an angle theta with the z direction, then it has two components. It is the parallel component, it is a perpendicular component, and it is v naught sine theta, and here it is v naught cos of theta. So here we are having these two components. So that means this equation is representing such type of motion. Now, keeping this thing in mind, what we will do, we will consider the motion of a charged particle in a say charged particle is moving in this type of right. So say in the middle, it is B naught is the magnetic field. Say at this point is Z naught. it is z-axis, and in the ends it is Vm. That means near ends, these are the two different ends, and this is the middle. The B naught in the center is very much, or in other words, magnetic field at the ends is very much greater than V naught. So if some particles trapped inside it, so that means it will try to go towards this, but it cannot escape out of it and then again reflect it back towards this direction. So that means charge gets trapped inside it. And this is nothing but this diagram is known as dual magnetic mirror geometry for plasma or charge confinement. Plasma or charge confinement. And if field is like this, then this can be mathematically represented as V naught 1 plus delta Z square. Such a field geometry is called magnetic mirror. So let us try to understand how this magnetic mirror or such type of things can be experimentally visualized. So if we are having this is a tube, and over which solenoid is bound in such a manner such that at ends the number of turns will be larger, right? So this is one end and this is another end. So where the number of turns will be large, magnetic field strength will be large, and where the number of turns will be less, where the magnetic field will be less. So it is V naught and it is Vm and Vm. So this is a way that how this magnetic mirror can be produced. So what this will do, this arrangement will produce a stronger magnetic field near the ends than the middle region. So due to this, if a particle moving in a lower magnetic field region, on penetrating into a region of increasing field, get reflected back into the region of lower field. So let B naught be the magnetic field in the mid region and Bm at the ends, and it will be the maximum value and it will be the minimum value. Now mirror ratio is defined as that R is equal to Bm over B naught. So now let theta naught is angle between velocity vector of particle and z-axis at z is equal to z naught, and theta be the angle between velocity vector of the particle and z-axis at any value of z. Then this kinetic energy can be written as 1 by 2 mv perpendicular square, or it is 1 by 2 mv naught square sine square theta naught, or it can be expressed as mu b naught, and say at any value of z this can be written as 1 by 2 mv naught square sine square theta naught. So that means this theta naught is replaced by theta, and this we can express as, and at any value the magnetic field will be B. So then if I divide this equation by this 2 by 1, so it gives us sine theta is equal to sine theta naught B over V naught. And if I try to express it in terms of means if Bm is at the ends and corresponding to it the angle will be this one at the ends with respect to ends. So this can be written as sine theta V naught over Vm raised to power 1 by 2 or 1 by r under the root. And this is known as condition for reflection of particle. This is the condition for reflection of particle. Condition for reflection of particle. Because what will happen, sine theta at ends, it get the maximum value. Maximum value means it will become 1. So from there it will become sine theta naught is with respect to ends, it is equal to B naught by B under the root. Means it gets reciprocated. This goes towards this side and this will become 1, and this causes this part. So that's why we have written in this form, and we have used earlier equation of magnetic mirror. So using that, this is nothing but this is 1 by under the root r. So this is the condition for reflection of a particle, and particle follows this condition, then it is reflected back, and with this the article of magnetic mirror will finish. So in the next lecture, I will talk about a relativistic motion of charged particle. So thanks for watching.